You know, when you see one of those massive industrial robots on a factory floor, moving with this incredible mix of power and precision, have you ever wondered what's really going on inside? Well, that's exactly what we're going to do. We're going to metaphorically pull back the metal skin and dissect an industrial robot to understand its anatomy from the inside out. You see, without all its key systems working together, a robot is just a lifeless hunk of metal and wires. So what is its anatomy? We're going to look at it not just as a machine, but as a system with distinct parts, kind of like a living body. So where do we even begin? Well, it makes the most sense to start with the part that actually interacts with the world, the robot's hands. The technical term for this is an end effector. This is the device, the tool, the gripper, whatever it is, that's attached right to the robot's wrist. It's what gives the robot its entire purpose, really. It transforms a general-purpose arm into a highly specialized worker.
Okay, so these hands basically come in two main flavors. First, you've got grippers. Their whole job is to grab and hold onto something. Then you have tools, which are bolted right onto the wrist to actually do something. We're talking welding torches, drills, you name it. So one holds, the other does. Simple as that.
And the ways they can grip things, it's actually pretty cool. You have mechanical grippers that use fingers, a lot like our own hands. Then you've got vacuum grippers, which use suction cups, perfect for picking up things like flat sheets of glass. And of course, magnetic grippers, which are, you guessed it, ideal for handling iron and steel parts. This variety is what lets a robot handle just about anything you can imagine.
All right, so the robot has its hands. But that's useless if you can't move them, right? This brings us to the core of the machine, its muscles and its bones. This is where all the power and movement comes from.
And this is where the whole robot anatomy thing really clicks. Just look at this breakdown. The robot's drives are its muscles. They provide the raw power. The transmission system, that's the skeleton, giving it structure and turning that power into precise action. And the control system, well, that's the brain, directing the whole show.
So let's zero in on those muscles, the drives. At their core, these are just motors. They can be electric, hydraulic, or pneumatic, and their job is to generate the force that moves the robot's joints. It's a direct parallel to how our own muscles contract to move our arms and legs. But just like in the real world, not all muscles are built the same. Electric drives are by far the most common. They're loved for their incredible precision and because they're clean. Hydraulic drives, on the other hand, are the heavy lifters. They use pressurized fluid to create immense force for really tough jobs. And then you have pneumatic drives, which use compressed air to make super fast, lightweight movements, perfect for quick little pick-and-place tasks. Okay, but all that raw power is totally useless without control and structure. That's where the bones, the transmission systems, come into play. We're talking about all the gears, belts, and screws that take the fast spinning motion from the motors and convert it into the slower, more powerful, and super precise movements the robot needs to do its job. They provide the skeleton and the leverage. Okay, we've got hands, we've got muscles, we've got bones, but what's the command center? What's pulling all the strings and telling everything what to do? That, my friends, is the job of the robot's brain, the control system. Now, these control systems typically come in two main varieties. An open-loop system is, well, it's like throwing a baseball with your eyes shut. It just follows a pre-programmed set of instructions and hopes it gets it right. But a closed-loop system, that's like throwing with your eyes wide open. It uses sensors to get constant feedback, and it's always adjusting its own movements to make sure it hits the target perfectly. Think of this closed-loop system like a constant conversation happening inside the robot. First, the controller, the brain, sends a command. Second, the actuators, the muscles, carry it out. Third, sensors measure what actually happened. And fourth, the controller compares the result to what it wanted and instantly corrects any tiny error. This little loop, repeating hundreds of times a second, is the secret to modern robotic precision. So how does the brain actually talk to the rest of the body? Well, it speaks in code. Programmers use all kinds of specialized languages like VAL or even more complex frameworks like ROS to write out the robot's instructions. These lines of code are basically its thoughts, telling it exactly what to do step by step. All right, so we've done the deep dive on the robot's insides. Now let's pull back and look at the bigger picture. Let's talk about the robot's place in our world, its environment, its ecosystem, and what it means for all of us. And believe me, their place in our world is huge. Right now, there are nearly 3.5 million industrial robots working away on factory floors all around the globe. This isn't some sci-fi future. It is the reality of how things are made today. And these robots don't just wander around. They live in these carefully designed spaces called work cells. A really common one is the robot-centered cell, where one big robot sits right in the middle, servicing a bunch of other machines around it. Or you have the inline cell. Think of a car factory, where robots are lined up along a conveyor belt, and each one does one specific job in the assembly process.
And the economic ripple effect of this whole robot ecosystem? It is absolutely massive. Robotization leads to these huge jumps in productivity and efficiency. You get more stuff made, it costs less to make it, and the quality is usually way better. For a lot of industries, it's just the key to survival. But, of course, it's not all sunshine and roses. We have to look at the other side of the coin. The rise of all this automation brings some really serious challenges. While yes, new jobs are created to design and maintain these robots, a lot of routine, manual jobs get displaced. And that can create real pressure on wages and brings up some tough questions about things like income inequality. And all of this, it brings us to a really big question. A question for all of us, really. We've taken the robot apart, we've seen how powerful it is, we understand its body and its brain. So as these machines just keep getting smarter and more capable, we have to stop and ask ourselves, what work, what decisions, and what skills should we decide must always remain uniquely human?